So our next speaker is Isabella, and then the paper is about adversities in abstract interpretation, accommodating robustness by abstract interpretation.
Put it like right on your.
Can you hear me? Okay. Okay, thank you. In this work, I will present an approach for modeling robustness for classifiers by abstract interpretation, in particular robustness against adversarial attacks. So let's start from the motivation of this work. In the context of classifier, we have this problem of adversarial attacks. We will see in a moment the intuitive meaning of this kind of attacks. But anyway, it is an issue, a security issue. And there is, in the literature, we found only an informal way of characterizing this kind of attacks. But anyway, a solution wasn't necessary. So during the years, several solutions were provided. But these solutions were given just based on this informal idea of what adversarial attacks were. And each one of these techniques, these are only examples of works where at least an informal way of describing what an adversarial attack is. In these techniques, usually the problem was that they were providing a technique for proving a property, for guaranteeing security against something that was not really formally specified. And in this context, some issues arise. In particular, for example, can we prove any relation between these techniques? I mean, if I have to decide which kind of technique to use for a specific application, how can I decide which is the best one for my context of application? And this is quite difficult whenever we have a definition which is informal, and each one of these techniques indeed enforce in different ways the same idea. Another issue is, for example, whether soundness is provable. I mean, how can I decide whether the notion I'm trying to enforce is indeed satisfied? And the problem is that since we don't have a unique formal characterization of this kind of attacks, it is hard just to understand whether we are really enforcing a universal, a generic notion of attack, and how we can really prove formally this aspect. So the way we choose is different. We try to provide a general formal model, a model which is as general as possible, just to capture these ideas and to have just a point of a reference point in order to attack these problems, to face these problems about relations or about soundness of these of different techniques that we can find in the literature. So what we propose is like a framework where we can, in some way, define, recognize as instances most of the techniques that exist in the literature, and at the same time, we can define some variants of the model that we provide in order to capture different features of the fields of application where we want to model the problem of adversarial attacks. So this is the context in which we move. And so let's start introducing precisely the problem. So we are in the context of classifiers. So what is a classifier that we consider? We have, for example, a cam that captures images, and the classifier has to decide which is the main subject of the image. So in this case, it says that it is a pedestrian. What is an adversarial attack? We have this image. We have our classifier that tells us which is the subject. For example, in this case, it recognizes that it is a road sign. But the problem is that we have also the classifier may depend on the definition of the image. So if we add some noise to the image, and this is what an adversarial attack may do, then we can deceive the classifier, inducing the classifier to classify with the wrong subject. So for example, in this case, it says that it is a traffic light, which is completely wrong. And this is the context. So we try to model formally this notion. And in particular, we consider an image, X is an image, and we take the set of a set of possible perturbation of this original image. And in this case, what we require is that whenever we have a class of the original image, then we require that also the class associated with the perturbation must be precisely the same. And this has to happen for all the possible images in the same class of perturbation. So this indeed captures the problem from a very simple and formal point of view, but in the moment that we can formalize the notion, this model can allow us also to understand whether this notion really captures all the possible situations that we can have in real cases. And indeed, for example, it can be in some conditions too strong, because if we have a perturbated image with a different class, then we would say that robustness is not satisfied. But maybe the two classes provided share some property that is acceptable. I mean, for example, if we have two images, an image of an animal, and the perturbation induces a classifier to classify the image with a different animal, but anyway an animal, maybe it is acceptable. So we want to capture also this information. Let's see an example. So suppose we have this road sign. Clearly, the right image is the giveaway classification, but maybe with a perturbation, it provides a different giveaway road sign. And clearly, there is a mistake, but anyway, both the signs are giveaway road signs, and both they induce the car to slow down. So maybe it is acceptable to have this kind of error in the classification. So the model is that we consider an abstraction, a property in the output classification. And in this case, what we require is that the perturbation, we are considering the abstraction of the class, so the general class that it represents. And we require that all the images that the perturbated image provide at least a class in the same abstraction. And this has to hold for all the possible images in the perturbation. Again, this does not capture completely the idea, because it can be, again, too strong, since we have introduced an abstraction, but we are not really exploiting the hierarchy structure that typically we have in an abstraction. So, for example, if we have that a perturbated image provides a class, a different abstract class, but we clearly don't have absolute robustness, but maybe this abstract class is more precise, is more contained in the class of the original image. And so maybe it can be acceptable again. So let's see again an example. Suppose to consider the images in terms of the actions that they induce on a car, for example. In this case, suppose the original image clearly is the giveaway, so it induces the action slow down or stop. And if we make a perturbation of the image, then the classifier is induced to say that it is a stop. In this case, the stop induces an action which is included in the actions of the original image, and it may be acceptable because the car makes at least a more restrictive action. So the model of this situation is what we call hierarchy-aware absolute robustness. And in this case, what we require is that the images in the perturbation must provide an abstraction which is at least contained in the original abstract class. And therefore, we require the property holds whenever for all the images inside the same perturbation, we have at least an element which is contained in the original class. Again, this is not the last step of our framework, because in this case, what happens is that we have a property that strongly depends on the center of perturbation, so on the choice of X. For example, if we just swap the rows of the two images, then the property doesn't hold anymore, since the original image is now contained in the abstraction of the perturbation. And clearly, this doesn't satisfy the property, but also, if you have a class which is not comparable, clearly the perturbation, the property is not satisfied. So again, let's see an example where this may be a problem. Suppose to have a classifier that decides which direction the car has to take. And in this case, suppose that it is acceptable from the image to take the direction, one of these three directions. It is acceptable to take one of these directions, but it is not acceptable to take the right direction. And in this case, as you can notice, the acceptable situations are not comparable. So we provide a new notion, which we call coherence. in which we require that, again, we consider the abstract property of the classification. And in this case, we accept as coherent a system, a classifier, when the perturbated image provides a class, an abstract class, which has a list per bound that is below the top. What does it mean? It means that in some way the abstraction, the output abstraction of the classes represents the degree of error that we are accepting in the classification. And the top for us means that we are just losing, we are mixing classes that we don't want to confuse, to mix. So for example, as you will see in the experiment, if we have an animal and a means of transport, then we don't want to just have a mixture, an error that takes one in the other. And this is interesting because it makes really a regional property. So now coherence is a form of robustness which is on a region of values and not on a single value. So, and this holds whenever it requires that for all the values, the image in the same perturbation, the list per bound of all the abstract classes that we have remain below the top, so it doesn't lose any information about the class. So the whole framework that we defined is this set of 4 definitions. We started defining the robustness. Then we allow a controlled error in the classification, so we admit an abstraction of the output classification. Then we introduce an exploitation of the hierarchy structure of the abstraction. And finally, we make the property a regional property with coherence. There is an implication relation between all these notions. So clearly, concrete is stronger than abstract, stronger than hierarchy aware. And in some condition, it is stronger than coherence, which indeed, usually they are not comparable. And also, whenever the abstraction is not a really structural, a really hierarchical structure, then also the inverse implications hold. So this means that it is really important to move towards this kind of characterization of robustness whenever we really have an hierarchical structure of the output observation of classes. We validated this notion. In particular, we started from the ATH robustness analyzer for deep neural networks, and we added the possibility to check hierarchy aware and coherence, just to experiment very quickly. In this case, we are in the MNIST data set, and which are images of numbers. And for X1, and the output error that we allow is just to obtain a number which is less or equal than the original number. And in this case, for the image X1 can be classified as 4. Since 4 is less than 9, then it is acceptable. On the other side, then the image X2 can be classified as 3, and this is not acceptable because 3 is not less or equal than 2. Another experiment on cipher 10. In this case, we are in coherence, so we have an abstraction of the output which has all the means of transports, which can be confused. There can be an error in the decision which is the precise means of transport that it is represented. And on the other side, we have all the animals. So, for example, in the image X1, the ship can be confused with an airplane. Since both are means of transport, that's OK. We don't reach the top. On the other side, we have a frog, but the classification can recognize it as a truck, which is a means of transport. So we have two values whose list per bound is the top, because we don't want to confuse this kind of images. So this is the framework. In the paper, we have also several characterizations of the domains and these properties. But in a way, which is the connection with programming languages, we have several properties in language-based security, in particular abstract non-interference, which is strongly connected with and inspired abstract robustness, and also the recently proposed local abstract non-interference. And there are several notions in static analysis, again, very strongly connected with this notion, in particular completeness, but also the recently introduced notion of adequacy, which was inspired in the opposite direction from coherence. So concluding, what is an ongoing work? We are defining a notion of approximate coherence, because coherence as it is, what we propose here is not a new technique for enforcing robustness. We are not saying that we made something better than others. It's just a model providing a different perspective on a problem and a way of looking at this problem in a formal way for making possible to compare and to better understand the problem of robustness against adversarial attacks. Among these notions, we think that coherence is the most interesting one because it is the really new notion and provides really a different way of looking at the problem. And the problem is that it is defined on a concrete classifier execution, which usually is too costly or uncomputable. And indeed, we face this problem in the implementation in Iran. So we are defining a new notion of approximate coherence, which is given directly in terms of the approximated execution of a neural network. So in this case, we perturb regions instead of values. And this can be important in safety because usually when safety is not satisfied, they make a refinement process, which is really costly. And if we are able to reduce the alarms due to a more precise representation of the problem, we can reduce this kind of refinement iterations. Finally, as future works, we would like to investigate the sensitivity. We can study the sensitivity of sensors against adversarial attacks. So how, by perturbing only some sensor, we have a different observation of the output. We can drive the design of class abstraction in finding out which are the actions that we can ignore since they are with low probability, as in the picture. And we also would like to understand whether it is possible to make classifier abstract robust, maybe by defining or exploiting a form of abstract training. That's all. Thank you very much.
Okay, thank you for the great presentation. Any questions from the audience? Here. Yeah, you can go ahead.
I was just wondering how fast it runs, how long it takes to compute one of these sets for a given input.
Sorry, I didn't understand.
How fast does it run?
How?
Can you hear? How fast?
Fast what?
Yeah. Like, so say I wanted to put this on a car. I get an image, and I want to compute the robustified set of things. Could I run it in real time? Does it take milliseconds? Does it take seconds?
The complexity of Iran, of the ATH, we don't add any complexity.
Okay. Is it like milliseconds? Is it seconds? Is it minutes?
Well, I have the table. I don't know. I mean, I have in the paper there are all the times, and it's acceptable time, really.
Okay.
I don't remember the seconds, really, but
okay.
It's computable in acceptable time.
Okay, I may have another question. So in those coherence properties, you typically need to have a substructure, right? Like some classification may belong to the same high-level class, but what if you have a classification problem, those substructures are not that apparent? So in this case, would this coherence property still be useful?
So you have a hierarchy anyway. I mean,
like you need to identify a hierarchy, right, in order to utilize those kind of coherence properties.
To have a significant property, you need a hierarchy, yes.
Okay, so basically, you need to analyze those hierarchy first in your first step.
I mean, at the moment, we have a hierarchy as part of the design. So it's the analyst, the analyzer, and the analyst in particular, that understand the problem and characterize the hierarchy that provides the kind of error that I'm accepting. One of the future work is to drive the design of this hierarchy from the problem. And that's open question.
Yeah, sounds good. Thank you. Let's thank our speaker again.